In this Applet lab activity, we will look at the relationship between theoretical and empirical probability. We'll investigate this question in the following two activities using coin flipping. So in this activity, or this lab, you will not need to turn anything in for this lab. Just work through the directions on this page and the questions below to understand the connection between theoretical probability and empirical probability. The purpose of this activity is to understand how the empirical probability relates to the theoretical probability. We will focus on the probability of H. In this case, probability of H stands for heads, instead of flipping and landing on tails. First, we will examine what happens with a fair coin. Then we will examine what happens with an unfair coin. So we'll use the applet below for both investigations. We'll go over the directions, and as we go, you can pause the video and follow along. So here we'll first talk about the first part here, part 1, a fair coin. We'll assume the coin is a fair coin. It's the likelihood of, or the probability of it landing on heads and the probability of it landing on tails is exactly the same. A single flip of a coin has an uncertain outcome. We do not know if we will get heads or tails. If we flip a coin 6 times, we are not guaranteed to get half of them heads, half of them tails. 3 heads, 3 tails. So what exactly does it mean when we say that the theoretical probability, the probability of heads, is 0.5 or 1/2? You have a 1 out of 2 chance or half chance. To answer this question, we'll use an applet above to simulate flipping a fair coin. So our first step will be start by setting the applet to represent the flipping of a fair coin. Set the probability of heads to 0.5. And as you can see, it already is, it's default at 0.5. For part 2, where it's not a fair coin, we'll change that, but for now we'll leave it the same. So now we'll set the applet, sorry about that, to simulate flipping a fair coin 3 times. Set coins to 1. So we're only flipping 1 coin 3 times, so I'm still keeping coins at 1. And then press the 1 flip button 3 times. So there should only be 1 coin, let's see. The number of coins can be changed here. Currently it's on 4. But I can go ahead and move that little cursor thing over to where I only see one above this little cursor here, and 1 coin, the little gold coin in the picture. Okay, now we'll press this button that says 1 flip. We'll press it 3 times, and then it should record how many of each you get, heads or tails. And now notice that for each flip, you'll see either heads 1 or tails 0. So that's the only confusing thing about this applet. It doesn't say T for tails, H for heads. It'll give you a 1 for heads and 0 for tails. Because we're trying to calculate the probability of heads. You get 1 for each heads and 0 for each tails. Because we're not interested in tails right now. Obviously, these are the only possibilities, so you will not see anything appear for values on the horizontal axis greater than 1 because you're only flipping 1 coin. Next, we'll estimate the theoretical probability of PH, probability of heads, for a fair coin using 3 flips. Based on your 3 flips, what is the estimate for probability of H? So use what you learned in the applet above. How many heads did you get out of the total of 3 flips? Calculate this by dividing the number of heads you got up there by 3. Why are we dividing by 3? Because there are 3 coin flips that we did. Next, the second estimate of the theoretical probability for a fair coin using 30 flips. So you've done it with 3 flips, now it's time for 30 flips. The more times you do something, the more accurate the probability will be. Press the reset button so that the count is cleared. So that way you don't see any heads or tails. It's like you've never done it yet. Keep coins at 1, so don't change that. And probability of heads to 0.5, don't change that either. Now press the 10 flips button 3 times so that you have 30 coin flips. This is easier than pressing 1 flip 30 times, of course. And the 10 flips button is here. Press that 3 times. You could, if you wanted to, press 1 flip 30 times, but that would be kind of silly. A second estimate of the theoretical probability for a fair coin using 30 flips. We did that. Now, part A. Based on your 30 flips, what is your estimate of the probability of H? We'll calculate that by just taking the number of heads you got in those 30 coin flips that you did. It should tell you the number. Divide that by 30. How close was that estimate of yours that you just did to the theoretical probability of 0.5? Obviously, we will not always get 15 heads out of 30 flips, which is exactly half. The histogram below shows the results for 12 of your classmates. Each small rectangle represents an empirical estimate for the probability of H from 30 flips. To check your understanding of this graph, identify where your probability of heads estimate would be on this histogram. So when you calculated that up here, the probability of heads is the number that you got out of 30, the number of heads you got divided by 30. So what number did you get? Some kind of decimal between 0.0 and 1.0. Where would it fall on here? Out of 12 people, 2 people got exactly 0.5, which is 15 heads out of 30 flips. It's shown in red above in that graph. Results ranged from 7 heads out of 30 to 23 heads out of 30. So estimates for probability of H ranged from 0.23 to 0.77. The average empirical probability estimate shown by the green triangle in the histogram was 0.497, which is very close to the theoretical probability. A third estimate for the theoretical probability. Now we're going to do another activity with the applet above. Press the reset button so that the count is cleared again. Keep the number of coins at 1 and the probability of heads at 0.5. Now press the auto button and watch the count of heads and tails change. Click the pause button once the total flips counts to 1,000. So on mine, I don't see the word auto, but I think this blank button here would actually do it. So if I press that, let's see, it'll start flipping and flipping until I pause it. The pause button is next to that button. Let's see, I'll circle it now. Here, because our we haven't gotten there yet, so I'm gonna let it keep going. Keep going. We're waiting until, let's see, this number here becomes 1,000. Right now it's 416, so I'm gonna let it keep going. Get ready to pause it. I mean, if it's close to 1,000, that's fine, as long as you're close. We're almost there. Oh, 1,001. Ah, close enough. Wow, I got almost a perfect... Our empirical probability is almost exactly the same as theoretical. Notice the number of heads I got was 501 out of 1,001. That's almost exactly 0.5. So I'm lucky. You might not have your number of heads and number of tails that close, but probably fairly close together because we flipped the coin 1,000 times. So if this were me doing this, even though I did 1,001 flips, I'm going to say 501 of them were heads out of, I stopped it a little late, so just whatever you got that was close to 1,001, and then I divide those and get something very close to 0.5. It'd be 0.5001 or something like that. Obviously, we will not always get 500 heads out of 1,000 flips, but we were very close, right? The histogram below shows the results for 12 of your classmates. Each small rectangle represents an empirical estimate for the probability of H from 1,000 flips. So now you notice that these are all more centered around the middle. Out of 12 people, no one got an estimate for probability of H that was 0.5, which is exactly the same as the theoretical probability. Results range from 467 to 509 heads. So estimates for probability of H ranged from 0.47 to 0.51. The average empirical probability estimate, shown by the green triangle in the histogram, was 0.491, which is very close to the theoretical probability. Which provides a better estimate of the theoretical probability? The probability of H for a fair coin. Either the empirical probability using 30 flips or 1,000 flips. Why do you think that's true? Okay, once you record those answers, now move on to thinking about an unfair coin. We'll start by setting the applet to represent the flipping of an unfair coin. We'll set the probability of heads to 0.2 to represent a coin that only has a 20% probability of landing on heads. We will repeat some of part 1 using the unfair coin to examine how empirical probability estimates relate to the theoretical probability of 0.2. An estimate of probability of H with an unfair coin using 30 flips. So first, let's go and change our probability of H being from 0.5 to 0.2 now. Let's go back up there. That was in this area here. We no longer want probability of heads to be 0.5. We want to move it over to 0.2. If we can get there, let's see. Just kind of drag it over until, there we go. Now we see 0.2. Okay, now let's go back and see what else they want us to do. So 2 of the 12 students got exactly 6 heads, which is 0.2. That's exactly the same theoretical and empirical probability would match. But many students did not. Results ranged from 3 to 8 heads, so estimates for probability of H ranged from 0.10, which is 3 out of 30, to 0.27, which is 8 out of 30, with an average of 0.18, which is a little over 5 heads out of 30. That's close to the theoretical probability of 0.2. Now we'll do another estimate as we did before with the fair coin, but now we're using an unfair coin. We'll do 1,000 flips. So press the reset button so the count's cleared. It's as if the coin hasn't been flipped yet. Now we'll keep the coins at number of coins at 1, and we'll keep the probability of heads the same at 0.2. Now we'll press the auto button, but as we saw, if your screen looks the same as mine, it's blank. Just press that empty button that's next to the pause button and watch the count of heads and tails change. Click the pause button once the total flips is 1,000 or close. Based on your 1,000 flips, what is your empirical estimate of probability of H? So just as before, if you didn't stop it exactly at 1,000, just do the number of heads that you got, whatever it was, out of the total number of flips. It should be somewhere close to 1,000, but it might not be exactly, because it's hard to stop it at exactly the right time. Okay. Obviously, when the theoretical probability is 0.2, we will not always get 200 heads out of 1,000 flips, which is exactly 0.2. The histogram below shows the results of 12 of your classmates. Each small rectangle represents an estimate for the probability of H from 1,000 flips. So let's look at that. Now you notice, just as with the fair coin, all the results are more centered around the theoretical probability. Out of 12 people, no one got exactly 200 heads out of 1,000 flips. Results range from 184 to 218. So estimates for probability of H ranged from about 0.18 to 0.22, with an average of 0.202, which is very close to the theoretical probability of 0.2. Which of those provides a better estimate of theoretical probability for the unfair coin? An empirical probability using 30 flips or 1,000 flips. Why do you think so? So what we'll learn from these activities, let's see. Here are the big conceptual points. So you'll write up what you thought in those last problems, all the questions that were asked before. So the big points here are, this activity helped us examine the relationship between empirical probability and theoretical probability. An empirical probability is an estimate based on relative frequency, a calculation of how often an outcome occurs in a long series of repetitions. It's based on data. A theoretical probability, on the other hand, is what we expect to happen. It's not based on data. When we examine empirical probabilities, on average, they do a good job of estimating a theoretical probability. There's less variability in the empirical probabilities with a large number of repetitions. In some situations, we will not know, or it is impossible to determine the theoretical probability, so we can use a single empirical probability as an estimate. In these situations, we are more confident about estimating the probability of an outcome using an empirical probability with a large number of repetitions.